Okay, so we built a skiing performance sensor and a data logger. We built this project because we were both passionate about skiing. That was kind of our initial motivation for the project. We initially wanted it to be like a heads-up display. We realized like some safety features limited us in that aspect. So we decided to go with a more no display, just a data logger that logs. So we have a couple of sensors on the actual device. We have a pressure sensor. This measures temperature, pressure, and from that we can calculate altitude. We have an accelerometer. This gives us analog outputs for X, Y, and Z axes. And then we also have a gyroscope, which gives us basically degrees per second of rotation. So the accelerometer operates with analog, and both the pressure and gyroscope we communicate by SPI protocol.
And there's also
a micro SD trans/flash breakout on the board, so we can output all of our data to a micro SD card and then put it into a comma separated value file format to visualize on a computer. So we did a couple test runs.
And you just did a test run in your car because there's no snow right now.
Right, yeah, so we couldn't actually take this out and ski with it. So we did a test run in the car. We started at the architecture school at Rand Hall on University Ave, and we went down to about Lake Street. And we chose this route because we wanted to visualize the altitude change. There was a steep hill, and we could also like open the windows, change the temperature. And so this was also interesting for us to see, to try to simulate a ski run.
Okay, and some of the data from the calibration run.
So some of the data we get after doing some correction work and integration to get velocity from the accelerometer and gyroscope gives us it's suspect data, but we can sort of see as we're going down the hill, we increase in velocity, and then we sort of come to a stop at the end, which is good.
But getting velocity is hard because you have to do numerical integration.
Yeah.
And there's always drift in the sensors and in the integration.
Exactly.
Right. So the fact that you could, but you're doing a correction based on linear drift.
Yeah. So when we did a number of tests having the device just sitting still so that we know that the velocity should be 0 over the course of an entire run. And seeing that data and the drift that we get after all of our integration and combining the sensor data, we see very linear patterns in the drift over time. So we try to correct for that in our movement data, and we get something like this. So there's a lot of work that could be done to try to improve this integration technique.
Well, let's see the temperature data and the pressure data.
So for that same run that Matt was just talking about, we see our altitude changing from what is roughly 187 meters down to, this says, oh please, well it's about 60,
you were saying
so 59, 60 meters.
So you're saying that there's a change of 110 or 120 meters,
right? And
that's actually what it is in
real life. And that's actually so these absolute altitudes aren't exactly correct, but that's the correct relative change.
Sure.
And the reason for that is that we don't have day to day the exact sea level
right.
air pressure in order to get the exact
right
relative. And then our temperature data for that car ride was also, so we had the car, heated and all windows closed, and we open the window here, and we can see the temperature start decreasing as the car cools off because it's obviously colder outside.
Okay, so all the sensors are working. You can log the data. You can clearly read it on a PC because that's what you're doing there. So next step is to make it usable on the slopes.
Yep.
All right, thank you.